Ashwin Deshpande. Mr. Ashwin Deshpande is country head India Intech Additive Solutions Pvt Limited. With an engineering background, he is MBA in marketing with over 2 decades of industry experience. Mr. Ashwin is involved in business development for 3D printing for automotive, aerospace, defense, and other manufacturing industries. Before Intech Additive, he worked with Altair Engineering, a global leader in simulation software, and Stratasys, a global leader in polymer 3D printers. Today, Mr. Ashwin will discuss on additive manufacturing 3D printing technology.
Thanks for all the panelists who have covered the basics and the details and applications and the need of Industry 4.0 and what it really means to either a large factory or a MSME or a small organization. So with the several elements of Industry 4.0, one of the elements being digital manufacturing, and within digital manufacturing we have additive manufacturing as one of the processes for manufacturing components. So I come from Intech, and I will take you through the basics of additive manufacturing, some the industries we are adopting those, and some of the applications and case studies. I'm not going to get into the basics of 4.0 because that has been very nicely covered by the panelists earlier. So what is additive manufacturing? It is a process of joining materials to make objects from three-dimensional model data, and that's where the digital part first comes into the picture, into the workflow. So you need to have a 3D CAD model, 3D model. It could be a scanned image of a body for implant manufacturing, or it could be a engineered CAD model used from various of the CAD programs. The process is making the component layer by layer, as opposed to subtractive manufacturing techniques, methodologies, which removes material to create a shape. The different types of additive manufacturing process. There are plastic technologies, there are ceramic technologies, there are metal technologies. Within plastic, there are several processes like sintering processes, extrusion processes, wet polymerization. In the metal, there are several processes like laser powder bed fusion being one of them, electron beam melting being one of them, energy direct deposition being one of them. Even there are binder jetting processes for binder processes for metal components, and so forth. So today my company has been developing metal technology based on laser powder bed fusion, and I will talk more about this process, which is being now, for the last 20 years, this technology has been there around, but the adoption we see now in the last 2-3 years has been increasing because the affordability has increased. More materials have come into the ambit of 3D printing. Customers are looking at options to reduce their carbon footprint, and the future looks, the compounded annual growth of additive manufacturing is around 25%. So that's a pretty good growth rates. So the industries who have been adopting or been using additive manufacturing predominantly for making prototypes in the design cycle before the parts are sent across for manufacturing for production, that is the production volumes. These are the verticals: the automotive, defense, aerospace, oil and gas, shipping, and you can read over here. Drones which are happening new, the unmanned vehicles. The academics has been one of the biggest users, and then some, the lifestyle industry is shaping up. There are a lot of demands for bespoke jewelry items, and that's where 3D printing finds a nice space for that. So predominantly the applications have been prototyping. They continue to be prototyping. Of course, the production applications are also there, and they are going, with the increase of production applications, the growth of the additive manufacturing industry is going to grow. Prototyping has a limited growth in terms of volume. So for the benefit of the audience over here, laser powder bed fusion, the process that we develop for the manufacturing components through the additive process, is a process where metal is melted. I will take the pointer. So the metal is melted with the help of laser. The heat source is laser, or it can also be an electron beam, but we use laser. And the powder is melted and then fused or welded to form a three-dimensional object. Basically, it's a melting and welding process. I'll play this. So you see the CAD model over here. So the user would take a decision on orientation, whether it has to build the part horizontally or vertically. Set up the process parameters like the layer thickness, select the material, the material. There are different kinds of materials which can be processed on AM systems in this metal technology. The alloys of steel, alloys of aluminum, alloys of titanium, alloys of inconel, and so forth. This is how the sparking happens onto the bed. The powder is laid. After one sparking of the layer happens, a recoater comes and lays another layer of powder, which can be in the range of 20 micron thickness layer, or 40 microns, or 60 or 80 or 100. And that's how a layer by layer part is built. And you see a part 3D printed. So coming to the process workflow, yeah, so the 3D printing process workflow works like this. You need to identify parts for 3D printing. As I said, when it comes to prototyping, it's pretty easy. Whatever parts, whatever designs I have made, I have to make a prototype for functional testing, physical testing, and then release those drawings for mass manufacturing. So identifying parts for prototyping is pretty easy. But it's not that easy when you are identifying parts for production applications. That's where a lot of experience comes into the picture. So the first step starts with identifying the parts for 3D printing. You need to have CAD models for that. For example, typically in the defense industry, let's say especially in India, since we have been buying hardwares from the European nations or the US, predominantly from the East European nations as Russia, Ukraine, and Czechoslovakia and so forth. These equipments have very long life, 30, 40 years of life. And sometimes, and now that we see, during these war situations or any other geopolitical reasons, the supply chains get disrupted. So we are left with only parts with us, which go through wear and tear. So that's where 3D printing comes into picture. But to get those parts 3D printed as a replacement item, scanning technologies come into picture. So we need to have 3D CAD models either through the scanning process or through grounds up process, that you from a 2D sketch you create a 3D model. Then before going for 3D printing, you may want to do simulations about the performance of the part based on the boundary conditions in which the part is going to function, it is going to operate, for its life cycles, for the loads that are going to be it is going to be subjected to. And once you're confident that the strength of the component is the stiffness of the component is meeting the end use requirements, you take the next step. You go to the machine, you select the material, you fire the part, then the part gets manufactured. You take out the part. Customer may be required to do some post processing on the net on the 3D printed part, like for example drilling holes. Not necessarily you have to drill holes every time, but you may be required to do that depending on your application. Maybe some surface finishing operations like short painting, buffing, and so forth. So some post processing may be required, may not be required, depending on the application. And then of course it goes to the quality and assurance, like what we saw in the previous presentation. All parts have to be checked for their tolerances and dimensional tolerances and quality, so forth, and gets into the use. So this is an overall high level process workflow diagram. This slide will explain you the cost and complexity comparison between additive manufacturing and conventional manufacturing. So when we say conventional manufacturing, we are talking about machining, we are talking about 2-axis machining, talking about 3-axis. We are talking about milling, we are talking about molds for plastic, pressure die casting, metal parts, extrusions, and so on and so forth. Well established processes, but if you look at the conventional manufacturing processes, when you are just take the example of making a prototype. Prototypes are required in very few numbers. Okay, maybe 10, maybe 20 at the most, depending again on the industry that we are working on. So going through the conventional process, it takes a lot of time, and the cost also is very high. But the conventional manufacturing scores high when you have millions of pieces to be done or lakhs of pieces to be done. So the cost of manufacturing is high for conventional manufacturing at the initial stage, but it keeps on going down as you go into the volume. As the volume increases, the cost keeps going down. Now, if you look at additive manufacturing, the line is pretty much linear, almost linear. It's a representative thing, but it's almost linear. It doesn't. So when you make one part in a machine versus 10 parts, the same geometry you 3D print one time, make it one. or make it 10, depending on the volume of the machine, the number of parts that can be nested into the machine or stacked into the machine, the cost pretty much remains the same. So at some point, so basically customers, when they are looking at additive manufacturing to be integrated into their production process, either for prototyping or spare part manufacturing or low volume production applications, they have to do a study about what kind of volumes they are looking at for those components, and arriving at a decision that, okay, till up to this volume, additive manufacturing gives them a cost advantage. Beyond that, conventional manufacturing will will give them a better cost advantage. When you look at this other graph, this basically talks about the complexity versus the cost. So if you would appreciate the in the video that we saw, a very complex bionic kind of structure, which is almost like impossible to machine or cast in the conventional manufacturing process, but 3D printing is agnostic to complexity. So whether you make a small whether you make a straight just a plate, or you introduce if there is a flower that you want to print, additive manufacturing does not recognize the complexity because it is manufacturing the component layer by layer. So complexity is free. So if you see in this diagram, in conventional manufacturing, the cost is very high for very complex products. So when we say complex, why do we have to make products complex? The moot question is why the another question could be that why our products are made simpler to manufacture, because it's very difficult to machine, it's very difficult to mill, it's very difficult to cast, because there you cannot have undercuts in the geometry. Now, why do we need complexity? If you look around in the nature, the most efficient designer in the world or this universe is the nature. There is no extra fat into those parts. They are not bulky. Wherever the material is required has been used by nature to deliver a certain performance. So when designers are allowed to design based on functionality and without bothering about without being bothered about the challenges of constraints of manufacturing, conventional manufacturing, you will end up coming up, the designs will become more and more complex and they are more feature rich. Okay, so with 3D printing, complexity is almost free. Okay, or rather free it is as compared to conventional manufacturing, and that's in a big way. So some of these reasons customers should be looking at in terms of volume and in terms of complexity. So one good example to probably understand, I'll try to show with some pictures, is why do we do joining? Why do we do assembly? Why do we add nuts, screws, bolts, rivets into a geometry, into a part or a product? Is just because we can't make them in one piece integrated, one integrated piece, one monolith. We can't do that conventionally. But what is the value addition of nuts, screws, bolts, rivets, and maybe other gluing techniques? The value addition is none other than increasing the labor cost, other than increasing reducing the structural integrity. Let's say primarily this could be the thing that we can look at, that why do I really need to have a nut, screw, and bolt into this geometry? Okay, can I make it integrated? Can I make it complex? And if I can really manufacture them, then 3D printing is the answer. And what volume I'm looking at? If my volumes are into lakhs, well, I better reduce the complexity. I still go ahead and do the several pieces and glue them together or join them together. So it's a good decision making slide. Just to appreciate this point, that you identify the parts for manufacturing or design for additive manufacturing is an important step in this evaluation process, that whether additive manufacturing can bring value to my enterprise, to the products that we are planning to launch and manufacture. So going from bulky shapes and a lot of material around, to finding out the best material layout. What you see over here is an optimized structure. The terms used for developing such structures through simulation process are called topology optimization or generative design. And you go and do your CAD modeling, then you do your finite element analysis, and then comes out your you have your final part that is manufactured and do so. So if you see such kind of structures, they're almost very difficult, if not impossible, they will be very costly to manufacture to the conventional machining or subtractive processes. So a design for additive manufacturing is a very important element when a customer is wanting to integrate additive manufacturing as a production process, not as a prototyping process. When you're looking at production parts, reimagining designs and so forth, then the design for additive manufacturing becomes an important element that the designers have to understand. Some things they have to unlearn, they have to learn new things. And we as a company with academic institutes in the country, we are working in that area of skill development and so forth. So kind of summarizing over here, additive manufacturing is the fastest manufacturing path from the CAD model to part. No investment in tooling. You don't have to make any molds and dies and jigs and fixtures and so forth. You can introduce designs very fast into the market. As we heard, the life cycles of the products are shrinking, have been shrinking. They'll continue to shrink till eternity. And so the best way to introduce new products is additive manufacturing, again subject to volume and complexity, because once you invest in toolings, you just can't change the product design in a short time, because you have to recover the investment in tooling. That is an important consideration for any enterprise. It's a near net ship manufacturing process, reduces additional manufacturing process. Material wastage is very less because it is creating a part layer by layer and not adding or we are not subtracting material and which goes otherwise waste in the conventional processes. Typically machining that we see, from a stock of, let's say, 10 kilogram, your end geometry could be maybe 2 kilograms. The rest of 8 kilograms is waste. That's not what happens in additive. Part consolidation, we talked about eliminating the assembly, joining requirements. So best for low volume production, high complexity parts. So prototype has been the last 20-25 years and 30 years, I would say. More than 30 years rather, this technology has been used for making prototypes. End-use parts is coming up now. For the last 7 or 10 years it has been there. Molding applications, so certain components of the molds are 3D printed. Jigs and fixtures are also getting 3D printed, or robotic grippers are getting 3D printed. Digital inventory is something which is like just in time. So today customers are maintaining huge amount of spares on their floor to service their equipment which is being used by the customer if the equipment goes down. 3D printing offers advantages where you need not maintain a high volume of physical inventory, or rather maybe it can be zero also, depends on the business case or use case, where the entire digital inventory can be there and you unlock your capital. And this is good news for the finance team, for the finance officers. And we talked about certain scenarios of defense organizations using long life, the product life cycles are very large. The components keep going through wear and tear, but there are no drawings available to these agencies because of supply disruptions in supply chain and so forth, and geopolitical reasons. So obsolete parts can be 3D printed through reverse engineering. And lightweight structures like what you see over here, it's a it's heat exchanger radiator, and then there are several lattice structure over here. Lattice structures are some, I can say they are very complex, but 3D printing can do it. Here are some case studies from India. This is Hindustan Aeronautics. What you see in the background are our machines. We are handing over a part to HAL Bangalore, a very complex component from a engine, the helicopter engine. Something unique about this case study was we developed their choice of material in a matter of few weeks, couple of 3 weeks, I would say 2 weeks, and a very unique case study. Then these are some case studies. This is a case study from the oil and gas sector, where if you see on this side of this picture, the holes which are over here, traditionally the holes have been drilled straight, because you can only drill straight holes. You can't drill holes in like a spiral. Okay, so the reason for going spiral holes was to reduce the sudden pressure drops, and reduce the wear and tear, and control the coefficient of flow. The best design the designer proposed was, if I can have a spiral flow channel for the fluid to pass through this cage in this valve, which is used in the process industry, I could have the best design. And that's where 3D printing came into picture, and some of our other softwares that we have developed came into picture. A brief slide about our company. We were the first company in India to launch metal 3D printing services, on-demand printing services, 2012. In 2017, we launched certain softwares for developing raw materials or process parameters for alloys, new alloys. In 2019, we launched a software that will drive our own hardware. So our hardware and software were launched together. The AM Builder, what you are talking about, so data preparation software. So our machines are branded as iFusion, and we are today we have achieved a decent amount of success in the country. So we are offering an alternative. So we are the first OEM in India to indigenously design, develop, and manufacture laser powder bed fusion machines. These are how our machines would look: a small format, medium format, and a large format machine. This is how they look. And just to tell you about the IoT, so all our machines are have a certain component of IoT in that. So when our customers are firing the machines at their factory, we pick up the signals from there, and we monitor the different parameters that determine if the machine is doing well, if the everything is right in the machine, and we if there is something that is an anomaly that the systems observe, it gives an alert to our technical support team, and we proactively go and we talk to the customer and tell him either to adjust certain parameters or certain settings, or if there is something going to failing, we would proactively order those parts and go and replace them. So and these things are monitored 24/7 at our factory, of course, whenever the customer machine is in operation. So we have implemented IoT in our machines, in our products. Some of the customers, academics, the defense organizations, the drone manufacturers, the aerospace startups, the automotive companies. This happens to be our customers. There are many more customers in India who are using different machines, predominantly imported machines. None of them had indigenous alternatives in the past, but last 2 years indigenous alternatives are available that brings down the cost and so on, with the obvious advantages of local manufactured products. Concluding slide. So as a company, we help customers in design for additive manufacturing. We develop new materials for developing new applications and meeting customer unique requirements, because every customer, every industry has different material requirements to meet their functional requirements of the products that they manufacture. Automotive requires different, aerospace require different materials. So we have a division and department which does that. Yeah, I'm concluding, and then so forth. So that's it.